So, welcome to the course on computational complexity theory. So, in IIT Kanpur, this course is numbered CS 640. Okay, this is a mid-level course. It's not very basic and it's also definitely not advanced. This is a course just after theory of computation. Um, if you have done that course, then some of the concepts here will be easier to start with. Otherwise, I will do a quick recap of the basic models like Turing machine, etc., time and space and other resources in the first week. And after that, we'll start building new things, new complexity classes. So, computation we all understand these days, and we all use in fact these days as a process running on a computer like device. So, even the definition of what is a computer like device keeps changing as new devices come up. So, previously phones used to be not a computer, but these days smartphones are actually as good as a computer, right. So, whatever is happening there, whatever is happening in that machine, that is really computation. So, it is a process, right, that can essentially solve any problem that can be solved, that can be automated. So, while complexity right. So, I am just defining the keywords which are in the course title. So, what is computation and now what is complexity? So, complexity refers to the resources that this process requires. Right. So, what are the resources? So, resources, the most common resource is time, right. How much time does it take to solve a problem? Like for example, if you just opened a browser and you are searching in Google. So, when you give a query, how much time does Google take to give you the results, right. So, that is time. So, time is what is important for you, and for Google what is also important with time is space. How much space does the algorithm require, because based on that Google will buy servers. So, these are the main resources. How much time, how much space, and you will see, or you must already be knowing, that the ability to toss coins is very important for computers, right. Many practical algorithms actually do random selection. So, in that case, how much of randomness? So, randomness could also be a resource, and in fact in this course we will invoke this a lot of times. It is a very important resource. So, the previous course, if you have done it, theory of computation, so this is motivated by the theory of computation. TUC is motivated by the question, does every problem has a solution? Now this solution, I not only mean mathematical solution, but also in terms of computing process, right? So problem may be a computational problem, and then you want to actually, you should be able to do a computational process, run a computational process on a computing device. So that is quote unquote solution that we are looking for. There is no mention of resources, time or space or anything in theory of computation. Right? That will be our business in this course. So theory of complexity is motivated by once there is a solution, once there is a process, what is the cheapest solution? Okay, so cheapest, it can be in terms of time or space or random bits and so on. So for example, we know how to add n bit numbers. Right, given via n bits. So this will be our usual mode of representation, that in the input you are given bits, right, 0 or 1. So A has n bits, B has n bits, and then these two integers you want to add. So obviously you know the addition algorithm from school. So there is a solution, but then how cheap is it? Is it a fast solution? So how cheap is this? Right, those kind of analysis we are interested in this course. So if we do it carefully, which means if we implement the addition algorithm carefully, then it takes time around, so I am skipping the constant factors in the from the implementation. So it will be something like n bits for A and n bits for B. So it's around 2n. Right? If you recall addition, the way it goes is you start from the lowest place, you add the 2 bits, then you get a carry. So you go to the next position. There now you have 3 bits to add, and so on. So it's kind of a single scan of these two numbers. Right? Obviously, every bit of A and B has to be seen, because if you flip even a single bit in your A and B, answer changes. So you have to look at 2n bits, and that is kind of the time complexity as well for addition. So this is as fast as it can be. Right? This is very cheap. So you cannot do it any faster than this. This is linear time. Right? You cannot do it faster than linear time, because then you would be missing some of the input bits, and that addition is very sensitive to that. So this is the example of a very simple problem, and obviously a very practical problem. I mean, you can do nothing if you cannot add numbers. And then there is the other extreme of very difficult problems, in fact problems that are impossible, like we have uncomputable problems. Okay, so there, I mean, the question of complexity would not even arise, because the problem has actually no algorithm. So then there is no resources required is infinite. Okay, infinite resources, you cannot solve it. So that is, for example, can you write a program that can read another program and decide whether it halts or not? That takes, let's say, a C program, M as input, and decides whether M on execution halts or not. Right. So whether the input computer program, and you can assume it to be C program, whether it will halt or not. So this is the famous or infamous halting problem. This cannot be solved. If you have done a course on TOC, then you already know the proof, but you can read the proof in standard text. It's quite easy, but very illuminating. Okay, another example is, so think of the program M as the following. So what I will do is, there is a for loop over even numbers. Okay, go over all the even numbers, use a flag, now go over primes, up to n, p less than equal to n, and check whether n minus p is also prime. Okay, we took a prime p less than n, and whether the remaining n minus p is prime. So if n minus p is prime, then you set the flag to 1. And yeah, so that's the second for loop. The for loop ends here. So I don't need to put the bracket. Let me just erase it. Okay, so go over all the primes and check whether for some p, n minus p is prime. If you find such a p, then you set the flag to 1. Otherwise, the second for loop continues. When this for loop ends, you will check for the flag. Whether it is 0, which means that no prime p was found, such that n minus p is prime. So then you will halt. Okay, otherwise you go to the next number n. So now this is a very short program, computer program M, which is basically, I mean, on the face of it, it's an infinite loop, it's looping over all the even numbers n, and it is trying to find, it is trying to express n as a prime plus another prime. Okay. So p plus q, can you express n as p plus q, where p and q are prime numbers? If it finds this decomposition, then it sets the flag to 1 and it will go to the next even number. If it fails, then it will come out, the program will end. So now the question is whether this program will halt. So this we don't know. Okay, we don't know whether this program will ever halt or not, or is this an infinite loop or not. So that is the level of our ignorance. So what you can show is this program halts at a counter example. Of the Goldbach conjecture. So this is a famous open problem. So what this program is trying to do, it is trying to find a counter example. Okay. When it halts, then the n at which it halted is of the type that cannot be decomposed into 2 primes. So, and we don't know whether such a thing, such an n exists or not. Goldbach conjecture says that such an n doesn't exist. So this program should never halt. So what this means, this small example, it is actually illuminating, because what it is telling you is that in this way we can encode almost any open math question. It's a C program. Okay, so you can express open math questions, mathematical conjectures as C programs, and then give it to the halting problem. So if you can solve halting problem, then you can actually prove math conjectures. It will be, solution will be automated, and so it is not surprising anymore that halting problem is actually unsolvable, right? So this seems incredibly hard. Right? The solution of all math questions cannot be automated. You would not expect that. So this problem is called this is the halting problem, which was this also in orange example 1. That was a general problem. So this general problem is called the halting problem. And it is known to be, it's provably uncomputable. Okay, there cannot be an algorithm solving this. So how is such a thing proved? right? If you haven't seen this before, you should wonder how can you show that a problem doesn't have a solution. So to prove this, one needs a rigorous definition of computation. Right, so a rigorous definition, a mathematical definition is needed, because otherwise you will be stuck with the microprocessor of some speed or a different speed, low speed, high speed, or the device, whether it's a smartphone, it's a laptop or a tablet or whatever. You don't want to get confused by the diversity of computational devices, right? So you want actually a clean and at the same time very general, most general definition of computing device, which is mathematically done, and then whether halting problem, whether it can solve the halting problem. Okay, that's the only way you can go about proving the uncomputability, by pinpointing what is meant by machines and what is meant by computation. So this is done on a mathematical model of a machine, which is the Turing machine. Okay, this is named, as I mentioned before, after Alan Turing. In 1936. Okay, so it was defined almost a century back, solving the question of what is meant by computation. So yeah, once you recall the definition of Turing machine, and once you define that by computation, we always means problem being solved on this Turing machine. Once you define it this way, then you can talk about complexity almost immediately. So this course will deal with various notions of complexity of problems that can be solved on a Turing machine. Okay, so we'll shorten this to TM. So problems that are being solved on Turing machine, we'll talk of its complexity in terms of the Turing machine execution. Okay, so that get rid of all these differences in the speed of computing devices and difference in the computer architecture, differences in the operating system or applications and so on. Okay, this will be the rigorous, clean and architecture independent definition of computation. So before I get into the definition, or before I recapitulate the definition of Turing machine and languages and problems, let me give a quick overview of the course. So let us quickly see an outline. So Yeah, so the first is discussing the halting problem. That's not really part of complexity, but I'll do it just to um, recapitulate important points about the Turing machine model, and then what can it not solve and how do you show it. And the proof, the idea of this proof is actually used in other theorems that we will do in this course called hierarchy theorems. So halting problem and the like. Right. For example, there is this Hilbert's 10th problem. So this is the problem of finding out whether um, a given system of equations has an integral solution. Okay, this is also called the Diophantine system. Whether the Diophantine system is solvable. Is there a root? Is there an algorithm that tells you whether there is a root, and if there is a root, find it. Okay, so that was asked by Hilbert whether there is such an algorithm. He had hoped that there is an algorithm, but then later on it was shown after many decades that actually this problem is uncomputable. Okay, halting problem reduces to this. So here is a very simple to define problem where halting problem, which is kind of completely unconnected, relates to. Okay, we'll discuss that. Then second is a very important problem. So I'm actually just going to list the problems, and according to the problems, new topics come up. Okay, you can think of them as major chapters. So second problem is that of SAT, which is short for satisfiability. So what is satisfiability? This is probably the most important open problem in computer science. It is given a Boolean formula phi in AND or NOT gates. So for example, it can be this x1 or x2 and x2 bar or x3, right? So x1, x2, x3 are literals, variables, and their complements are also allowed. This you achieve by the negation gate, and then you are ORing them or doing an AND. So either you do disjunction or conjunction, right? So phi in this example is a conjunction of two disjunctions. These disjunctions are called clauses. So there are two clauses. You are doing an AND. Satisfiability question, as the name suggests, is whether this formula phi is satisfiable. Okay, can you assign x1, x2, x3 true false values such that phi becomes true? That is the meaning of satisfiable. So decide whether phi is satisfiable. Okay, so that is the question of SAT. That is whether there is an assignment xi true false such that phi is true. So this is where everything starts in complexity theory actually. Okay, the simple problem on Boolean formulas. In fact, computers use these gates and or NOT gates. So it's inspired from there, and whether this formula is satisfiable. So this will define the most important question in complexity, which is, or in general computer science, and then finally also in math, whether P is different from NP. Okay, we'll get to that when we do this chapter. Third problem, let me correct the spelling. Third problem is QBF, quantified Boolean formula. So quantification means that you either do a for all or there exist on the variables, right? So satisfiability you can think of as using a there exist on all the variables, right? Does there exist x1, x2, x3 such that phi is true. But now you can also use for all, so you can actually mix and match. It's like there exists x1 for all x2, there exists x3 such that phi is true, right? So now we are given quantified Boolean formula. So given a formula with quantifiers, there exists for all. Again, an example is phi equal to there exists x1, there exists x2 for all x3. The same formula that you had before, which is x1 or x2, x2 bar or x3. Right. So instead of asking whether there exists x1, x2, x3 assignment, we are now saying that does there exist assignment for x1, x2 such that no matter what you fix x3, which means true or false, the formula remains true. Right. So is it true in this example? Can you set x1, x2 so that independent of x3 both the clauses are true? So yes, you can do it. You can just you want to basically x2 bar, you make it 1, you make it true, right? So you can set x2 to 0 and you can set x1 to 1, and that will make x2 bar to 1, and then x3 doesn't matter, right? x3 can be anything. Since x2 bar is already 1, which I mean true, so both the clauses are true, your formula is true. Okay, so in this case phi is indeed true. Maybe I use a different variable. So that this is the question of computational question of QBF. So decide whether psi is true. And when you study this in that chapter, we will define a new complexity class, and the question will be NP different from P space. So I am just telling you the questions. Okay, here the question is whether P is different from NP. Whether you can solve SAT, that's the question of P not equal to NP. Whether you can solve QBF, we will show that QBF actually can be done in polynomial space, so it's in P space, but can you do it faster? Okay, so that is kind of the question of P different from P space or NP different from P space. Those are the questions. So these are practical questions, but out of practical questions, we will actually come up with complexity classes. Okay, will not, when you define a complexity class and you ask these questions, you are asking a question about infinitely many problems instead of just one problem. Okay, that is kind of the interesting thing about complexity questions.